Okay, good afternoon, everyone. So first of all, let me thank the organizers for giving me this opportunity to be here. So I would be talking about active magneto gyrator and some of its interesting aspects. So first of all, let me acknowledge my PhD students, Musin and others, as I am presenting a part of their thesis work. And also let me acknowledge the DST Government of India for financial support through the SARBSURE and CRC grant. So first, let me briefly introduce what is a Brownian gyrator. In a Brownian gyrator, it's actually a fundamental system in which a Brownian particle is confined by an asymmetric potential, harmonic or parabolic kind of potential, and it is coupled with two heat baths which are kept at two different temperatures. And if it is the case, such a system will generate a systematic gyrating motion of the particle across the potential minimum. So that's why, since the gyration of the particle is possible only due to the presence of potential asymmetry and temperature gradient. So that's why it is termed as Brownian gyrator. So the potential asymmetric potential, it can take of this form with alpha as the potential asymmetry. Such a system it has already been verified experimentally by several groups. These are the possible experimental setups. So, but even if the system is having potential asymmetry and temperature gradient, still, if the principal axes of the potential, for example, like this principal axes of the potential, if it do not coincide with the temperature axes, like y prime and here x and x prime, these are the principal axes of the potential that coincide with the temperature axes. In that case, the gyration will not possible. So particle will simply diffuse across the potential minimum. So for generation of the gyrating motion of the particle across the potential minima, so the principal axes of the potential should not coincide with the temperature axis. That is what is happening here, and as a result, the system exhibits a systematic gyrating motion of the particle, as well as there is a systematic rotational current. So, since the system exhibits a gyrating motion across the potential minimum, so the particle exerts a kind of torque on the confining potential. So one can utilize this gyrating motion by loading the system in a direction opposite to the torque or in the same direction of the torque. And in fact, this has been experimentally, such a setup has been experimentally verified as a minimal model to work as microscopic heat engine. However, very recently, these groups, they investigated such a system in the presence of magnetic field. And what they observed that when they are loading the system in a direction opposite to that of torque, then the system can work as a heat engine. And while while loading the system in the same direction of the torque, then it can work as a heat pump. So what we took interest that if we investigate such similar kind of system, but considering the motion of an active particle instead of a passive particle, then what will happen? So this is because the activity can add an additional layer of control of duration of activity and the performance characteristic of such systems. So for that, in our work, what we did, we just investigated the two-dimensional motion of an inertial charged active Ornstein-Ulbach particle, which is confined by a two-dimensional asymmetric harmonic potential, which takes up this form with alpha as potential asymmetry, and a magnetic field is applied in a direction perpendicular to the plane of the motion. And further, the whole system is subjected, it is coupled with two heat baths which are kept at two different temperature, Tx and Ty, along the orthogonal directions, and the whole system is subjected again to a viscoelastic environment. So the motion of the particle can be described by simple Langevin equation, where the viscoelasticity of the medium can be realized by a viscoelastic drag force with Ft minus T prime as a friction kernel or viscous kernel, which contains a delta correlated time correlated delta function, and also a time dependent memory kernel, which is considered here as a in such a way that it will decay exponentially with a time constant Tc prime. So Tc prime is considered as a is the time up to which the system, the environment possesses some memory, or this is the can be considered as a memory time scale. So so this is the viscoelastic drag force, and this is the force exerted by the confining potential, and this is the Lorentz force due to the presence of the magnetic field, and this is the active force which is basically here considered, which especially it follows Ornstein-Ulbeck process, as per which, sorry, this is Ornstein-Ulbeck process, as per which there is a finite correlation in the medium, and that correlation decays with a time constant Tc. So the Tc is basically the time up to which there is the system exhibits activity. So it can be considered as the time up to which the particle can self-propel by its own. So this is can be considered as an activity time scale. And this is basically the delta correlated white noise. So with such a setup, the system exhibits two mechanisms. One is the gyration of the particle due to the presence of potential asymmetry and temperature gradient. And another one, there is also precession effect due to the presence of activity and activity and magnetic field. So in order to investigate the effective gyrating behavior, what we did, we have exactly calculated the orbital magnetic moment and analyzed the magnetic moment in various circumstances. So first we consider the case of viscous medium. So viscous medium means in the absence of the environment or medium does not possess any memory. So that can happen mathematically if we take this limit, Tc prime tends to 0 limit. So in that case, so this is the exact result of the magnetic moment. So first, in the case of pure precession, that means in the absence of gyration, that can happen either in the absence of the potential asymmetry or temperature gradient. So in that case, we observe that the system is completely paramagnetic. And when in the case of pure gyration, that is in the absence of precession, that can happen either in the absence of activity or the magnetic field. So we observe that this is the case of a normal Brownian gyrator, and the system exhibits a magnetic transition from diamagnetic to para or vice versa through a non-magnetic line, and that non-magnetic line leads to the state of the system where the system approaches thermal equilibrium. So this is consistent with the Bohr-Brmlin theorem or classical equilibrium system. But when in the presence of both gyration and precession, what happens? So the system still exhibits a magnetic transition. So I'll just take 1 minute. Okay, magnetic transition, but it happens through a non-magnetic line for which the system is driven away from the equilibrium. So that is the case. That means even if the system is away from equilibrium, then still the system is non-magnetic or magnetic moment is 0. So this is all about the viscous case. But when the system is subjected in a viscoelastic environment, and we analyze the behavior in both behavior of the magnetic moment in the memory and activity parameter space, what we observe here that the whole regime is dominated by a dimagnetic phase with a very small paramagnetic phase for higher values of Tc prime and for a finite regime of the activity, duration of activity. And with increase in this temperature gradient, the paramagnetic phase expands towards both the lower as well as higher values of Tc. But what happens that when the temperature gradients become 0, that means in case of when in the absence of the temperature gradient, unlike the case of viscous medium, here we see that there is a dimagnetic phase still exists in the lower regime of Tc, activity, lower duration of activity, and that is possible only due to the presence of memory. So here it is confirms there is a, due to the viscoelastic environment, there is a memory induced dimagnetism. And what happens that we further increasing the temperature gradient, so this dimagnetic regime shrinks And the non-magnetic line that forms a closed loop starts forming a closed loop with the diamagnetic phase inside the loop, and the paramagnetic phase completely surrounded by that loop. So that is a kind of trapped diamagnetic phase due to the memory. So this is a kind of memory induced trapped diamagnetic phase. And what happens that we further increase in the temperature gradient, this phase disappears. That means this diamagnetic phase, the effect of the diamagnetism, that is completely cancelled with some of the gyrating effect. So that's why this phase disappears and the system becomes completely paramagnetic. So this is a interesting results which we have published recently. So this is like if you subject this whole system in a viscoelastic environment, so you are having a kind of memory induced trapped diamagnetism. So further we have investigated about also the performance characteristic of system and how it responds to the presence of viscoelastic memory and so on, but I will not have time, so I will quit it here. So thank you for your kind attention.
Time for questions. Any questions? Okay, if there is no question, then please thank the speaker.